All right, so this is for IM1, LP7, days 15 through 19. So we're going to be looking at some more sections in chapter 12. So as always, I start off by looking at the class expectations. Sorry, that got scooted down a little bit there. Just make sure you're logging into Alex. Yes, you should be logging in on a regular basis. I know I suggest in class all the time, it should be every day. The more you work on math, the easier it will become. The more we kind of put it off and try to do spurts of math, it's going to stay kind of that same level of difficulty because we're just not practicing enough. So just make sure, log in often to work on math. Homework, tests, topics, and quizzes are all the categories. Yes, you have some every week. We're not doing any homework in class this week because I'm not there to help with the homework assignments. So we're taking the notes and then doing all the homework on alex.com. Topics, tests, and quizzes we always do on alex.com because we just don't have time to do those in class. So all work is submitted by Sunday, and yes, you can ask me for extensions. It will lock you out Sunday at midnight. So I know I've been stressing that a lot in class lately, that if you log in at 11:59 at midnight, if that's the last day for that assignment, it will lock it out. So just don't wait till the very last minute to start working on your homework. Your resources, so make sure you have your teacher. That includes your math teacher and your independent study teacher. You have your notes pages, and I gave you your notes pages ahead of time for this week so that you can go through and fill them out from this video. You have the in-center tutor. We have the FEV tutoring. That's 24 hours, 7 days a week. Alex actually has explanations, examples, and its own videos on quite a few of the different homework assignments and topics within there. I'm also made videos for all of the different homework assignments. It's at the top of the first page of each of the notes pages for the week. So that's the QR code, or you could just go to a Google Classroom if it's been shared to you. I also have the link to the YouTube page if you need that. You can also ask questions directly to your teacher from alex.com, which is very convenient because we know exactly where to go to help you. All right, so we're going to be looking pretty heavily at proofs this week. And a proof, when we're completing a proof, we're not just going through the steps of a problem to find, the value of X or something along those lines. What we're doing is we're going to be given certain information, and then we have to use that given information and what we know already about the presented diagram to get to the prove part, what kind of our end goal. And in order to do that, we have to be able to plan ahead a little bit on proofs. It really does require planning ahead. So we're going to go through and we're going to look at all of the different reasons that are available to you in Alex on these proofs. And I'm going to go through kind of one at a time, just reading through them. The more you study these, the more that you pay attention and really try to remember them, the easier proofs will become. I'm not requiring my students to memorize them by any means, but the more you can study them, the easier it will be for you to look at a problem and kind of visualize, where am I going? If you're only ever looking at this list kind of during the problems, then it's going to be a little harder to visualize that path. All right, so we have all right angles are congruent. So if two angles are right angles, then they are congruent. That is, their measures are equal. And hopefully that makes sense, because if we have two angles that are right angles, even though this one looks larger and this one looks smaller, both the angles are 90s, because that's what right angles mean. Now, when we call it a right angle, we're actually talking more about the shape than the measurement. But we also know that when we talk about the shape of a right angle, the measurement is 90 degrees. So angle 1 and angle 2 are congruent because right angles are congruent to each other. All right, so the second one, we have vertical angles property. We use this one all the time. Anytime you have lines crossing like this that make kind of an X, you can use vertical angles. So if two angles are vertical angles, then they are congruent. That is, they have equal measures. So it doesn't explain to us what they are, just that they're congruent. So if we come over here and look at the vertical angles from the diagram, we have vertical angles theorem states that in a pair of intersecting lines, the vertical opposite angles are congruent. So Our only requirement is that we have lines that are intersecting. Literally, they cross like an X. And what it means by opposite, the vertically opposite angles, is going across the vertex. It's not really about vertical. That sometimes students get a little confused about that word because vertical, means straight up and down. But it can be from side to side also. Really focus on the vertex. That's kind of a better way to think of it. It's opposite vertex angles, which we have to be careful about that because, all of these are vertex angles. So that's why they don't name it that way. But we can go across left to right. We can go across up or down. If it was more diagonal, we could go from kind of a diagonal version of this. So we can see down here we have that angle AOE. So AOE, that's this left angle here, is congruent to angle BOF. So BOF, this right angle here. And then AOF, so AOF, oops, going too far. AOF, that's the top, is congruent to BOE. BOE. If you notice, the vertex that creates the angle is always in the middle. So I know I'm saying AOE because I start on one of the kind of ends and move to the vertex and then go to the other end. But O is the middle. That's actually the angle on all of these because O is the vertex on each one of them. All right, so vertical angles are congruent. A linear pair property. So if two angles form a linear pair, then they are supplementary. That is, the sum of their measure is 180 degrees. So what is a linear pair? It's literally two angles that make up a line. So we can see there's a line along the bottom, and we have another line here that kind of split the angle. So a line adds up to 180 degrees if we have just the line. Well, if I have two angles on a line, then they add up to 180 degrees. All right, we have the triangle angle sum property. And yes, we are definitely going to use this one a few times. We're going to look at some triangles. And this is the sum of the angle of the measures of a triangle is 180 degrees. So if we look at this diagram over here, we have angle A, B, C. And if we add A, B, C up, we get 180 degrees. This one you can actually see, there's a little animation that goes with this one as well, where you can actually see that it's these three angles. If we put them together like this at the top, they would be a line. So actually it comes directly from the linear pair property and also parallel lines property, because this line created at the top would be parallel to the line at the bottom. So it's a couple of theorems kind of put together there. That's where the triangle angle sum theorem comes from. All right, now we have the exterior angle property. We reviewed the triangle angle sum property last week. We just learned the exterior angle property last week. So these are some pretty current, I can say current, so pretty current things that we just went over. So the measure of an exterior angle of a triangle is equal to the sum of the measure of two remote interior angles. So if we look at our little exterior angle theorem property over here, we have this exterior angle over here. And what it means is I took the side of the triangle and I extended it. I just kept drawing. And it creates this angle on the outside of the triangle, so exterior angle. And this angle will add up to the same thing, or will be equal to the remote angles, the sum of the remote angles. Sorry, I'm saying that funny. The sum of the remote angles. And I like the word remote interior angles because the purpose of a remote is that I don't have to, like if I'm using it for the TV, I don't have to get up and touch the TV. I can sit on the couch and change the channel. Same kind of idea here. We have angle D that's out here, and it's remote from A and B. It's not touching these two. So it's touching this one, right? That would be the linear angle with it. But there's these other two angles on the inside that it's definitely not touching. And we call those the interior remote angles. So if we add these two up, A plus B, we'll get this exterior angle. This comes directly from linear angles, because we have a linear angle here that would add up to 180 degrees, and the triangle angle sum theorem, because these three, this little one we don't know, and then A and B would add up to 180 degrees. So we're adding this unknown angle here to both pieces of that. If I add this unknown angle to this exterior angle, I get 180. If I add this unknown angle to these two interior angles, I get 180. So I'm adding the same thing to these two quantities, which means they must be the same. If I combine these, that it must be the same as this one if I'm getting the same result. So it's a combination, again, of these two theorems so that we can skip over a step. That's actually what it's for. All right, we're going to keep going here. So we have, these are the ways to prove triangles congruent, and we are definitely going to use these in these proofs because it's all about proving triangles congruent today. So we have SSS congruence property, and that stands for side, side, side. So it says if the sides of one triangle are congruent to, which means they have the same length as, the sides of a second triangle, then the triangles are congruent. So pretty much if we have 3 sides of this triangle congruent to 3 sides of this triangle, the 2 triangles are congruent. We have SAS congruence property, which stands for side, angle, side. So if 2 sides and the included angle of one triangle are congruent to, again, meaning having the same lengths and measures, 2 sides and the included angle of a second triangle, then the triangles are congruent. So if we look at the little diagram here, we have a side, angle, side. So I'm literally reading them in order. It goes the left side, whoops, sorry, uncovering stuff again. So the left side, the very next angle, and then the bottom. And the angle is actually created by the 2 sides, inside, angle, side. So the 2 sides we're referring to create the angle in the middle. So that's what included means. It's in between or created by. In between is kind of a little bit better description to me. So we literally have side, angle, side. I can just read it this way. That other one I just covered up, we can see it says ASA, so angle, side, angle, congruence property. This one is just a little, it's kind of same wording as the last one, but instead of 2 sides and the included angle, now we have 2 angles and the included side. So we can look at the little diagram here and I can see I have an angle, a side, and an angle. And the side is in between the 2 angles we're referring to. So again, included means in between. It's a very easy way to refer to it as in between. So I have angle, side, angle. And so if 2 angles and the included side of one triangle are congruent to 2 angles and the included side of a second triangle, the 2 triangles are congruent. All right, and then we have one more of these guys. It's angle, angle, side, congruence property. So this one is a little different because it's if 2 angles and a non-included side of a triangle are congruent to the corresponding 2 angles and side of a second triangle, then the triangles are congruent. So now we have a non-included side. So we can look at the diagram here. We can see we have angle, angle, and then side. The side comes after the angle. It's not in between. That means it's included. This would be in between the 2 angles, but it comes after the angle. So I go angle, angle, side. We don't go angle, side, angle when we do angle, side, angle, which is this guy here, we don't skip over this angle here. So I wouldn't go this way and go angle, side, angle, because I skipped over a side, I skipped over an angle, so that wouldn't work. So be very careful. You want to kind of read them in order that way. When you do angle, angle, side, you do skip over the included side. All right. So takes a little bit of time to get used to using these. We're going to practice them quite a bit in the next few steps here to see if we can kind of get through as many as we can. This is the last really big one that we're going to go over, I believe. So this is cpctc property. And we like to shorten it because it stands for corresponding parts of congruent triangles are congruent. So it means that once 2 triangles are proven congruent, so once we've already showed these 2 triangles are congruent, we know this, then the 3 pairs of sides that correspond must be congruent, and the 3 angles that correspond must be congruent. So we can use this at the end of a proof to show that either angles or sides are congruent. So this is the continuation step. This is the next step. After we've proven triangles congruent, we can use this theorem or this property to show specific angles are congruent or specific sides are congruent. So it's how we keep going after proving triangles congruent. And we're going to practice this one a few times in the second section for today. I'm saying second section, but it'll be section 5 because we're going to do section 4 first. Oh, okay. We have a couple more of these guys. So addition and subtraction properties. These are for any real numbers a, b, and c. If a equals b, then we'd say a plus c equals b plus c. Or a minus c equals b minus c. So really what we're doing is we're just saying I can subtract or add the same thing to both sides or subtract the same thing from both sides. As long as I'm adding or subtracting the same thing from both sides of the equal sign, I haven't changed the equation. So that's what the addition and subtraction sign tells us. I can add the same thing. So in this one, they're adding a to x and a to y. So it's still equivalent. It's still equal. Or I'm subtracting a from x. I'm subtracting a from y. So they're using different letters on, the little poster board here, but it's still the same idea. As long as I'm adding or subtracting the same thing from both sides of the equal sign, I haven't changed the equality. So they still equal each other. We also have that same idea for the multiplication and division properties. So again, I have a equals b, and as I'm multiplying by c, so I have ac equals bc, and down here I have a divided by c equals b divided by c. So same rules as addition subtraction. As long as I'm multiplying or dividing by the same number on both sides of the equal sign, I have not changed equality. So these use the exact same letters on this one instead of kind of changing it up with the poster here, but we're just showing that I can multiply by c, I can divide by c, or any number, whatever it is. In this case, they're using the same letters. Definition of perpendicular. So whenever you're given the words perpendicular, bisector, if they use the words parallel, sometimes we're going to have to define these words. What do they mean? How do we know we can use them? So the way that we use that given information is to define it, and then we can move that into another step. So two segments, rays, or lines are perpendicular if and only if they form right angles. So that's angles that measure 90 degrees at the point of intersection. So if I'm told that lines are perpendicular, I know they equal 90 degrees. They form right angles. So first I would say, if they told me that the two lines were perpendicular, I would say that the angle is a right angle because that's the definition of perpendicular. Then I could say that the angle equals 90 degrees because that's the definition of a right angle. So I could actually get 2 steps out of that if they told me something along the lines of, the red line was perpendicular to the blue line. Reflexive property. Any time we have shared pieces in a diagram, we're going to use the reflexive property, and we're going to use it quite a few times today. So for any real number, a would equal a. Or for any geometric object, a is congruent to a. So anytime I'm using the same object, we're going to focus more on geometric objects. And a lot of the time it's triangles that are sharing the same line. They're kind of butted up against each other. So as long as they're sharing the entire line, we know that side is congruent to itself. And we'll see that in action here in just a moment. All right, we have the transitive property. And this one's a little different because it's kind of like a jump property. That's a little bit how I like to refer to it. So either way, if we're looking at the real numbers or geometric objects, it's the same idea here. So we have a equals b, and b equals c. Well, then a equals c. And so the idea here is that we're kind of going from a to c from beginning to end. So we're jumping over the b part. If I know a equals b and I know b equals c, then I can just ignore the b and go straight from a to c. So I like to refer to it as the jump property. Substitution. For any real numbers a and b, if a equals b, then a may be replaced by b or b may be replaced by a in any expression or equation. Not sure why I put that diagram there. That's interesting. Yeah, that diagram does not have to do with substitution necessarily, unless I we could go through and actually look at it and say if EF is equal to HG, then I could replace HG with EF, or the same thing with AB and CD if I'm looking at these geometric objects. But these are more like congruent lines than objects, or substitution property. These would go with congruent lines. But substitution, just anytime I know what something equals, I can replace it with that. So I'm trying to remember, we may use that in some of the proofs today. All right, so we have definition of congruent segments. There we go. That's why. It just shouldn't have popped up quite yet. So definition of congruent segments. Two segments are congruent if and only if they have the same length. So we have these tick marks show us length. So 1 to 1 means that these two small ones are congruent. So EF is congruent to HG. And then we have 2 to 2. AB is congruent to CD. So you always match up the tick marks. And that was another thing that we started practicing last week. Definition of right angle. So I kind of already brought this up. If an angle is a right angle, or an angle is a right angle, if and only if measure is 90 degrees. So if I'm told that it's a right angle, then I know that it's at degrees 90. If I'm told it's a 90-degree angle, then I know it's a right angle. So I can kind of go back and forth with that definition. All right, let's go ahead and get started on our first proof here. So Alex has a couple of different versions of proofs. The first one it always kind of starts us off with is these fill-in-the-blank ones. And then we're going to move to proofs where we fill in every single line on the statement and the reason. So they always kind of start you off with these fill-in-the-blanks to get us started here. So we're going to use the given information to prove that triangle ABC is congruent to triangle CDA. So we have ABC, this top triangle, and then we have CDA, kind of the bottom triangle. And we want to prove that those two triangles are congruent to each other. So we had those 4 theorems that helped us prove congruence. So we have, in this case, we're looking at just this first section today, which is 12.4. And specifically, this section is about side, 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 and side angle, side. So it's pretty likely those are the ones we're going to focus on because this is the first section we're really looking at those 2 theorems kind of closely. So first, let's go ahead and label some given information here. So we have AB is congruent to CD. So AB is congruent to CD. So I can see that marked. I have my tick marks up here. So the left and the right side are congruent, and then I went ahead and added it down here to the proof. It's the reason that we put it in the proof is because it was given to us. Quite literally, it says given. I wouldn't have known that. I could have guessed at it, but I wouldn't have known it for sure if they didn't give it to me. And then the next one, same thing. We have BC is congruent to DA. And the only reason I know that I'm putting it in the proof is, again, it was given to me. So BC, there it is. I was going to say where are my hash marks. So I have 1, 2, 1, 2. So 2 to 2. I'm doing color coding, but I'm also doing the number of tick marks to keep that straight. You always want to make sure that you're using number of tick marks, not just color coding, because if by chance we lost the color, like if it was printed and it was printed in black and white, you would no longer be able to see red or blue. They would just all look the same. So you want to make sure that you're using the number of tick marks so that you can tell them apart, even if you lose the color on the document. All right, so with this one, the way that we're going to prove this congruent is either by using side, 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 or side angle, side. So we're going to have to show that all 3 sides of one triangle are congruent to all 3 sides of the other triangle, or 2 sides are congruent and we have 1 included angle that's also congruent. And for this one, since I don't know anything at all about the included angle here, because remember, since it's in between, it means it's included. It would have to be this one, B and D. I'd have to be able to prove something about those angles right now. Well, there's nothing I can prove about them. They're not telling me anything about parallel lines, which would be the only way that we could really mess with the angles as far as congruence goes. So I'm not going to focus on the angles. What I'm going to focus on is this line that they're both sharing, because they both use this segment AC in the middle here that I made pink. So AC is congruent to itself. AC is congruent to AC. So this is what I was talking about when I said we're going to use that reflex property quite a bit. Anytime you have a diagram and the triangles are kind of smashed together like this, and they're both using the same segment, definitely use that to your advantage. That's going to be the reflex property. And they already told us that down here anyway. Just because since this is fill in the blank, it kind of helps us move forward just a little bit. So I know AC is congruent to AC. So now I have all three sides of triangle ABC are congruent to all three sides of triangle CDA. I just proved all three. I have red to red, blue to blue, pink to pink. Right? So now I've done my job. I've proved all three are congruent, and I should have typed that CDA so that they're in corresponding order, but that's all right. It's in corresponding order down here. Be careful about how you type those in, because if we don't type them in corresponding order when we do have to type them in on the next one, it will mark you wrong for not typing them in the right order. So if I would have been able to type it in down here and I typed in ADC, it would have actually marked me wrong because that's not corresponding. A on the top triangle does not correspond to A on the bottom triangle. A on the top triangle corresponds over here to C on the bottom triangle. So you want to be very careful how you type them in. And the reason that we were able to prove that is because of side congruence. All right, so the very next one we're going to do, they don't give us any hints here because we don't have any fill in the blank. We're just going to go through and start looking at what did they give us and how do I get from my given to my prove. So first thing, always start labeling the given. So if QR is congruent to SR, and I put that on in the proof because it was given to me. So here we can see it. QR and SR, those are the two kind of right sides there. And then we have PQ is congruent to PS. So I'm putting that down here in the diagram again, or in the table, because it was given to me. And here you can see it's marked again. So I have PQ and PS. And those are kind of the left-ish sides of the diagram. So this is very, very similar to the one we were just looking at. Remember, we have two options. I can either prove that all three sides are congruent or the three sides in the included angle. And again, I'm not given any information about these angles out here, which would be S and Q. Those are the ones I would need to be congruent to be able to use this, because it has to be that included in between angle. So I'm going to focus on this third side, which is shared by both of them. It's just like that last proof. They both use PR. Well, I know that PR is congruent to PR. They both use that entire segment. So I'm going to go ahead and use that. PR is congruent to PR, and I know that it's equal to itself because of the reflex property. All right, so now I have done my job here. I've proven that all three sides of triangle PQR are congruent to all three sides of triangle PSR. So the two triangles must be congruent by side congruence. All right, so now over here, you can kind of see this one starts out, it's a little bit longer. I think the last one was only 4 steps. 1, 2, 3, 4, 5 steps. So to prove two triangles are congruent, we can show that 3 sides are congruent or 2 sides in one angle are congruent. So if you notice, that's a pretty common theme here. I'm reusing those 2 theorems over and over and over again. So that's my job, is every time I want to make sure that I'm doing that. I also throw these little hints on the worksheets. You know, does the figure have a shared side or a shared angle? What does bisect mean? Because now we have bisect in here. So whenever we're given a word in our given, we're going to have to define that. And then mark all the given information to determine if we will use side, or side, angle, side. So let's go through and mark our given information. So we have AB is congruent to BC. So we're going to put that in our statements as our given. So it's our first piece. We have to put the given in there, because even though it's stated up here, if we don't put it in our statements and reasons down in the actual table, it doesn't exist yet. We have to put it in the table. So if you don't state it down here, then it doesn't exist. You can't use it. So that's why we have to go through and state all these pieces. So the next one is BD bisects triangle or angle ABC. So I have this line here. This blue line is bisecting an angle. So we have to define this. And again, I know this because it was given to me. So now I'm going to go through and I'm going to define angle bisector. And I know it's bisecting an angle because it says it bisects angle ABC. There's also segment bisectors. They both do kind of similar things. They're cutting that object in half. That's what bisect means. So an angle bisector would mean that it's cutting this triangle or this angle ABC in half. So I have these two pieces where you can see these pink arcs, and the two angles will be congruent because I'm cutting it in half. So now I can put it down here. I can have angle ABD, so that's the first one, ABD is congruent to angle, I should have wrote CBD, but I believe Alex would be okay with you writing DBC. It's not always as picky about the corresponding order of little pieces like this. It's more picky when we get to the actual triangle congruence. But I should have gone in the same order. I'm usually a little bit more picky about that. So since I started on the outside, ABD, I should have started on the outside and gone CBD, just to keep that consistent. And I know that because of the definition of angle bisector. If I have an angle bisector, it means it cuts the angle in half. All right, so both triangles use the segment BD. We can see that again. It's between both of them. It's what's kind of creating the two triangles, this line. So if they both use BD, then BD is congruent to BD. I can use that reflex property again. Anytime that line is shared, or sometimes we do have an angle that is shared by both. I don't think we're actually doing that in any of them today. It's all lines that are shared. So anytime you see that line shared, use the reflex property. All right, so now we can see on our diagram I have side, angle, side. So I have the red tick mark to the very next angle to the blue line. And the angle is created by AB and DB. It's created by the lines I'm talking about. So this is side, angle, side. And same thing on this other triangle we have here, side, angle, side. So the two triangles are congruent because we just showed that two sides of triangle ABD and the included angle are congruent to two sides and the included angle of triangle CDB. So we proved exactly what we set out to prove there. The two triangles were congruent. This time we're using side, angle, side. Because I don't know anything at all about these bottom sides. I can't prove it until after I've shown the triangles congruent. Now the triangles are congruent, I can prove any part congruent to its corresponding part. But before that, I have to use previous knowledge to prove the triangle's congruent. All right, so now we're moving to section 5. And if you've noticed, this changes to angle, side, angle, and angle, angle, side. What I've noticed about this section, though, is every once in a while they will still use side, 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 or side, angle, side because it's previous knowledge. We've already learned it. So now they're open to be able to be used, honestly. So we can use any of the four on these ones. I know for the first couple in particular, we're going to focus on angle, side, angle, or angle, angle, side. But once we move toward the end of this section, it's kind of a free-for-all based on the diagram, whichever one fits. So with this one, same idea. We're going to go through and we're going to start to label our diagram. So we have ST is congruent to UT. We're going to put that down here in our statements. And we already know we're putting in here because it's given. The next statement is just the next given. So we have our next given statement here. And this time we're given that angle RST is congruent to angle VUT. And again, I'm marking it on my diagram so that it's a little easier for me to follow. The next thing they want us to do is look at another angle. And they even, because it's with a fill in the blank idea, I have a little hint on where to go. It's the vertical angles property. So I'm going to look at where these two lines cross because that's what vertical angles are. So anytime we have a diagram like this where I can see the two lines crisscrossing, I can definitely use some vertical angle property there. So if I'm looking at the vertical angle, here we go. It kind of jumped a little bit there. So we have the two angles inside of here. So we have RTS, which is this side, RTS, and that's going to be congruent to VTU, because these opposite vertical angles are congruent to each other because of the vertical angles property. So we just showed that two angles of triangle RST and an included side are congruent to two angles and the included side of triangle VUT. So I have angle, side, angle, angle, side, angle. And if you notice, I am matching up the colors here. So when I say angle, side, angle, I went blue, red, pink. And when I did on the side, I did the same thing, blue, red, pink. So you want to be able to match up those corresponding parts. They should be in the same order. So we can say the two triangles are congruent because of angle, side, angle congruence. Alrighty, so now we're going to go to no more fill in the blank. We get to fill in all the pieces here. So again, we can use any of the four theorems at this point to prove these triangles are congruent. This diagram looks pretty similar to the last one, so we're going to go pretty much the same direction there. So we have DF is congruent to HF. So here it is down here in my statements, and I marked it on my diagram, and I'm putting it down here in my table because it was given to me. So that should always, always, always be your first step. The next one, I have two angles that are congruent to each other. So here we have them marked on the diagram, and here they are down here in the statements, and I'm putting them down here because they're given to me. So now that we have our diagram marked, we can kind of decide where to go from here. Without knowing anything about the lines, unless they were telling me that lines were parallel, there's nothing I can prove about, angle D and H. I can't really prove anything about any of the sides. So I can see, though, that I'm making this cross, right? There's this X in the middle. That means I can use vertical angles. So I can prove something about that angle. It's really the only way I can go at this one. So we're given one side and one angle, and we cannot prove anything more about the sides, right? That's what I just said. There's really nothing more that we can do there. But we can prove that angle. So we're going to look at vertical angles. So if I go across the vertex here, I have angle DFE is congruent to angle HFE because vertical angles are congruent. All right. Oh, that wasn't supposed to disappear necessarily. There we go. Just needed to come back here. So we just showed that two angles and the non-included side of triangle DEF are congruent to two angles on the non-included side of triangle HGF. So we just proved angle, side actually on this one. Angle, side. The side's not in between, it's after the two angles. So they are congruent, but this time it's angle, side instead of angle, side, angle. I know we're using kind of the same parts there because it's two angles and a side with either one, but you need to pay attention to where is that side. Is it in between the two angles we're talking about or after them? So this guy definitely goes angle, and then I run into the side. So it's angle, side, angle, side. All right. So, oh, interesting. I wonder what those little blue pieces are for. Hopefully those don't need to be part of the diagram here. So again, we're going to go through and figure out which of the four will we be using. And I can see this word bisect again, so we're going to have to deal with that once we put it into our diagram. So first, let's go ahead and mark our pieces. So we have EF is congruent to GF. And I'm putting that in my table because it was given to me. I have to put it there, though. If I don't put it there, I can't use the information. Next, I have DF, so this line in the middle here, bisects angle EFG, so kind of this bottom angle. If I looked at the whole angle here, it's bisecting. So let's put it on our statements, and we're putting it down there because it's given. So now let's define angle bisector again. Remember, angle bisector means it's cutting the angle in half. Okay, so we can see that we have these bottom two angles here, and I know it's kind of overlapping funny. I should have lined those up a little bit better, but we have this one at the bottom, GFD, is congruent to EFD. So we have these two angles that become congruent to each other because the blue line cut the bigger angle in half, the whole thing, chopped it right down the middle. Kind of like if you were looking at, you know, a funny shaped sandwich, I guess, and you cut it from corner to corner. And we know that because of the definition of angle bisector. As soon as I hear that an angle was bisected, I know it was cut in half. So, and half means that the two pieces are the same. So both triangles also use the segment FD. So FD is congruent to FD. So again, I can see, and as soon as I put that bisector in there, hopefully that kind of helped alert you. They're both using that line, FD. So FD is congruent to FD. I'm going to use that in my statements and reasons. And I know it's congruent to itself because of reflex property. Okay, so we just showed that two sides of triangle DEF and an included angle are congruent to two sides in the included angle of triangle DEF. So we just did our job. And as you can see, we're kind of jumping backwards already. And we're not using one of these two, because it's two sides in the included angle. So I know they're congruent, but it's by side, angle, side. So even though this section is labeled angle, side, angle, and angle, angle, side, those are previous knowledge. So we're able to use those if that's how the diagram works out. So that's why it's very important at this stage to make sure we're practicing these and we're studying them so that we know they're going to keep coming back. And even theorems and postulates definitions that we don't normally use, they're sometimes kind of arbitrary, they do end up coming up every once in a while. So it's very convenient if we already know them and we don't have to look those things up. Because if we're not really aware of those smaller things that sometimes pop up in a theorem or proof, then it's a little bit harder for us to kind of pull that knowledge and reference it. All right, so we're going to go ahead and try another one here. So again, we can use any of the four. And we're going to use the given information to prove that the two triangles are congruent. So first, we have SV bisects RU. So here's our line SV, and it's bisecting RU. So I'm going to put that in my given here. Here's what I was given, and my reason I wrote it down was because it was given. Let's go ahead and define a segment bisector before we jump to the second given. So I can't really use just SV bisects RU. I need to say, okay, what does that actually mean? What does segment bisector mean? Well, it means it cuts the segment in half. So that means it went right through the middle here. This point is the middle of RU. So RT is congruent to UT, or UT is congruent to RT if you say it that way. So it cut that in half. It gave me two smaller segments that are the same length, which is the definition of segment bisector. And now we have information on the two separate triangles. Before, I just had one line that was going across both. That's giving me information, but it doesn't actually tell me any congruencies between the two. All right. The second piece we have here is that RS is parallel to UV. So, and I just made them blue. Usually we actually see arrows on these ones, but I wanted to kind of visually see the color a little bolder there so that you could see that the two blue lines are parallel to each other. And parallel lines, we did this quite a few weeks ago, those have a lot of special qualities to them. Once we know that the lines are parallel, now we have all these other properties we can start to apply. Corresponding angles are congruent, alternate interior angles are congruent, alternate exterior angles are congruent, same side interior angles are supplementary. So we have to go back and remember all of those pieces, and those weren't in the list necessarily when I went through the beginning, but we did go through all of those properties just a few weeks ago in class. I think that actually might have been our snow week when we were not in the center for our center that week. So there was another video that went out about all of those properties. If you haven't watched that one yet, definitely go back and watch it so that you understand how all those properties fit together. So again, we wrote this down because it was given, and now I have to use parallel lines because that doesn't really tell me anything about them. There's no congruency there, but I can use them to prove congruency. So we can prove angles congruent. So I can show that these two angles are congruent, the ones I marked here in orange. And we call these alternate interior angles. If you notice, they're on different sides of the red line. So this one's kind of on the bottom. I know it overlapped a little. And this one's on the top of the red line. The red line is what we call the transversal. It means it crosses both the parallel lines. So that when we're talking about alternate, that's what we mean by alternate. If If I say same side, I'm also referring to the transversal. Those words are describing where they are on the side of the transversal. So they're on alternate sides of the transversal, and they're in between the parallel lines. So I'm kind of bouncing back and forth here in between. So this would be outside of the parallel line if I went outside. This is in between, right? They could close on the mouse there in between. So these are alternate interior angles. And if I know the lines are parallel, alternate interior angles are congruent. So I can go ahead and say those two angles are congruent to each other and literally just go down my list and say, if two lines are parallel, then alternate interior angles are congruent. Make sure you're choosing the correct one, because there's going to be two wordings here. There's going to be one that says, if two lines are parallel, alternate interior angles are congruent. There's going to be another one that says, if alternate interior angles are congruent, the lines are parallel. So we're starting with parallel lines and moving to alternate interior angles. If you were given alternate interior angles and moving to parallel lines, that's when you'd use that second one. So just be very careful. Each one of these has two that look very similar. They just switch kind of the beginning and the end. But we're looking for the beginning with parallel lines and moving to alternate interior angles being congruent. All right, now we could use this again. We could actually kind of switch the transversal because RU also crosses both the blue lines. So I could do this again, and I could prove that this top angle is congruent to this bottom angle here by the exact same property. Or I could use vertical angles like I have in the past. So I can go across. So this one actually has two different paths you can go with. Just depends on which one you like the best there. So as we're going through, I went ahead and did vertical angles. I know there's one other one just like this one where I'm going to show you using the alternate interior angles twice. So definitely there's more than one answer here, and there's more than one path. This is not the only way to type this information in. I could have very well typed this blue line in first, and then the second one could have been the red line, and then the third one could have been the pink line. As long as they're in a relevant order, and I don't need something before I stated that. So before I can talk about definition of segment bisector, I need to state that we have a segment bisector. But I don't need to state parallel lines before or after either one of these. It doesn't have anything to do with these. But before I could state this orange line here where the two angles are congruent to each other, I need to say that I have parallel lines. So some things are dependent on other pieces, while others are not. They're kind of separate from each other. So it's all about just making sure you're paying attention to that order as you go. All right, so we have our two vertical angles here going across the vertex. We have VTU and STR. So I know those are congruent to each other by vertical angles property, or vertical angles are congruent. So now I've shown that two angles and the non-included side are congruent to two angles in the non-included side of RST are congruent to UVT. I forgot to say RST for the first one. So I have angle, angle, side. So the two triangles are congruent by angle, angle, side congruence. All right, so now we're going to go through two more proofs here for this section, and we're going to use this property. So I brought it back up again because we haven't used this yet, and it's definitely a little bit to get used to shortening it like this. But we never write out corresponding parts of congruent triangles are congruent. It's just kind of, a lot to say. So even on ALEKS, you're going to see it as cpctc. And remember, this is after we've proven the two triangles congruent, which is what we've done on, I think it's 5, 6, 7, is it 8 proofs now that we've just done? So we've been proving all these triangles congruent. This is what we do after that point. So once I've proven the triangles congruent, I can go back and show that any of the corresponding parts are congruent. So I can go back and say, okay, well, triangle PAT is congruent to triangle JOG, so I can match up corresponding parts here. Angle P corresponds to angle J, and I can see that because it's got two tick marks here and two tick marks here on the arc. It's a different way of marking the arc there. They're doing one arc with tick marks across the arc. I've also seen it as just multiple arcs. That's usually how I do it. Or I could match up side lengths. I could go PT, well that has 3 tick marks there. So JG also has 3 tick marks. That's matched up. Now, not all our diagrams aren't always going to be matched up perfectly like this as far as already marked out, but we can match up these corresponding pieces so that we can show every piece has a matching or corresponding part to it. All the angles have a corresponding angle, and all the sides have a corresponding side. All right, so let's go ahead and use that. So again, first we're going to prove the triangle is congruent using one of our 4 pieces here, our 4 properties or 4 theorems. So let's go through the same thing. We're going to mark our diagram. BC is congruent to DC. So let's put that in our statements and reasons. We are also given that AB is congruent to AD. So again, let's put that down here in our statements and reasons. And I should have put 2 tick marks on here. I just must have forgotten to do that. Darn it. I was just talking about that earlier, not just using the color coding. So we have our given information here. So now we have to decide what to do next. So we're given 2 sides are congruent. So we can either prove that a 3rd side is congruent or that an angle is congruent. Something about the angles. Because the only thing using 2 sides is going to be side, 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 which is that 3rd side that we need, or side, angle, side. So that's that angle we would need. So if we go back to our diagram and kind of just think about it for a minute, I can't prove anything about the angles right now. B and D look congruent, but that's not enough. I can't just say, well, B and D are congruent because I think they're congruent. We have to be able to prove it. And there's nothing I can use right now to prove that. So instead, let's focus on the side. And again, they share that middle line, that AC line there. That's going right through both of them. So that's the 3rd side of both of them. I can prove that it's congruent to itself using the reflex property. So I just proved that all 3 sides of triangle BAC are congruent to all 3 sides of triangle DAC. We just use side, side, side. All 3 sides are congruent. So the 2 triangles are congruent by side, side, side. This is where we're not quite done yet. We're going to do one more step because it didn't ask us to prove the triangles were congruent. It asked us to prove the angles were congruent. So this is where that cpctc comes in. Now that the angles are congruent, I can use corresponding parts of congruent triangles are congruent. So if I look over here and I go BAC, that's this angle here, and DAC, that's this angle here on the top, those are corresponding to each other because it kind of looks like I just folded this guy down, right? They're just kind of mirror images of each other there. So they are in the right order there. This bottom one is corresponding to this top one. They are congruent. And I can even see that when I wrote this out, BAC and DAC, well, if I just switch those to angles, they're still in corresponding order. So it's actually kind of nice that I put them in corresponding order that way. So I can go ahead and say the 2 angles are congruent to each other because they're corresponding parts of congruent triangles. All right, let's try one more of those. So same deal. We're going to go through and prove the triangles are congruent and then use that information to go a step further and prove, in this case, 2 sides are congruent to each other. So let's go ahead and mark some given information, and these tick marks shouldn't have quite popped up yet, but that's okay. We'll get there in a moment. So QT bisects PS. So here's QT, and it bisects PS. So that's why those tick marks were there. They should have been on the next slide here, or the next part, but that's all right. We'll forgive my animation there for a moment. So QT bisects PS, and that's given. Now we're going to define segment bisector, which is where those tick marks come in. Segment bisector means it cuts it in half. So if PS is cut in half, then now it's PR and SR. It's the 2 pieces. And they're congruent because that's the definition of segment bisector. That means it cuts it in half. All right, now we have our next piece here. We have parallel lines again. So PQ is parallel to ST, and I marked it just with the blue line so we could see that. Again, a little bit. I wanted that to pop a little bit more than just the arrows that we normally use for parallel lines. So I'm going to put that down in my diagram here. And again, parallel lines mean I'm going to go back and use one of those properties of parallel lines and transversals. Corresponding angles are congruent. Alternate interior angles are congruent. Alternate exterior angles are congruent. Honestly, most of the time when we have these, we're going to be using alternate interior angles. That's the one I've seen the most. So we're going to prove some angles congruent here. So let's go and see where I put these. So I have these two orange angles that I just marked. So remember, the red is the transversal. That's on the cross of the two parallel lines. And I've marked angles that are on alternate sides of the transversal. One's kind of on the top here, one's on the bottom. And then we're in between the parallel lines, so alternate interior angles. So I know these two angles are congruent because if the lines are parallel, then alternate interior angles are congruent. Make sure you're paying attention to which one of these you're selecting again. All right, we're going to do that again. Instead of using vertical angles this time, we're going to use alternate interior angles again. So I'm just going to flip over to these other two angles here. Now my transversal is PS. I know it's not lit up. I don't have it, or colored up, or however you'd say that. I didn't bold it with a colored line. But PS is this kind of gray one going through, and it's crossing both the blue lines. It's another transversal. So I can use alternate interior angles again. So I have these two angles are congruent because the lines are still parallel, so alternate interior angles are still congruent to each other. So now I just showed that two angles and the non-included side of triangle RST are congruent to two angles in the non-included side of triangle RPQ, the top one. So I have angle, angle, side. So this one, remember that it's not included, so we wouldn't say angle, side, angle. That's included. I go angle, angle, side. So I want to be careful about which one of these we choose. They sound very similar, but that order matters. So I have angle, angle, side congruence. Now that I've proven the triangles congruent to each other, corresponding parts must be congruent. So PQ, and if I look at the way I listed this, PQ, that's the second letter and the third letter. If I come over here, I'm going to go second letter and third letter, which is ST, which is exactly what I want to prove congruent. So that's why the corresponding order matters. We should be able to grab them first to first, second to second, third to third, and that's angles. Or if I grab them two at a time, RS would correspond to RP. ST corresponds to PQ. So I should be able to grab them in that same type of order there. So we're going to use corresponding parts of congruent triangles are congruent to prove that PQ is congruent to ST. So my reason is just cpctc. They are not going to write out all of the words. They always have it shortened. All right, so we're going to move forward. We're going to do a couple not proofs, and then we're going to do one more proof. So I know not proofs. So we're going to review really quick equilateral, isosceles, and scalene triangles. This was another thing that we started to go over last week. So we're just reviewing it. So finding side lengths and angle measures of isosceles and equilateral triangles. So we'll review names and properties of the three types of triangles. So we have equilateral triangle has three sides that are congruent. So we can see that over here. All sides are equal. If a triangle is equilateral, it is also what we call equiangular. This means that we would divide, that should be 180, into three equal pieces, which is 60. That was just an oops on my part for the typo there. Each angle would equal 60, but we would divide the 180 equally into three pieces. So equilateral, equiangular, those are kind of interchangeable words. They mean different things. Equilateral means equal sides. Equiangular means equal angles. But if a triangle is equilateral, it is equiangular. If a triangle is equiangular, it is equilateral. So if we have one, we have the other. All right, and then we have isosceles triangle has two sides congruent. So we can see that image in the middle here. We have two sides are equal, so we can see two tick marks to two tick marks. And this only has one, so that means it's kind of the odd one out. But we have the left and the right side are congruent. So we call that an isosceles triangle. So we have a couple pieces when we get isosceles triangle. The last one here is the scalene triangle. Remember, that means that no sides are equal. That's just our third type of triangle. But if we have an isosceles triangle, the base angles opposite the congruent sides are congruent. So that means if I go on this side, if I go opposite down here, and then I go this side opposite down here, those two angles are congruent to each other. And we're going to practice this, and I'll have some arrows to kind of show you a little bit more what I mean by opposites. And then if we start with two congruent angles, so if we start at the angles, then the opposite sides are congruent. So this is the isosceles triangle theorem, or the converse of the isosceles triangle theorem if we're starting with the angles and moving to sides. So let's actually look at a problem like this so I can show you. So with this first one, we're going to use the information that they're giving us, so the markings, and if you're not sure what the markings mean, that you can click on this on Alex and it'll actually explain the markings again to you. But I bolded the red markings here, so they showed us that all three angles are congruent. So this is what we call an equiangular triangle. That means that all three angles are congruent. So we can see that. I bolded them, right? So that means that all three sides are also congruent. So we can go opposite sides. If this side is 5, that means that everything across from that same angle in that same figure are going to be equal. So HI in this one is 5. If we look at this one, now we have 12 and 12, so we have an isosceles triangle. We don't have an equilateral triangle, but we can still use that opposite angles idea. So I went opposite to 80, opposite, well that must also be 80, because they're both 12. So the angles opposite the congruent sides are congruent, and we call those base angles. If we started with the two angles congruent, I could reverse the arrows and go to the sides to prove that opposite sides were congruent. Alright, so now we're going to look at a little bit of algebra with this piece. So suppose that triangle FGH is isosceles with base FG. Suppose also that the measure of angle F equals 3x plus 9 degrees, and the measure of angle G equals 4x minus 6 degrees. Find the degree measure of each angle in the triangle. So I don't know anything about H, but I do know something about F and G. And I want to fill in all three angles. So I also am given some markings here. That they told us it was isosceles, and then down here in the diagram they show us which two angles are congruent. Remember, isosceles means at least two sides are congruent. So if I know that those two sides are congruent, then the two angles opposite those sides are also congruent. I'm using that isosceles triangle theorem. So I'm going to simply write this out as an algebraic expression, or equation, not expression, sorry, equation, showing that 3x plus 9 is equal to 4x minus 6. They're the same. They're equal to each other. They're congruent. So now I'm going to go through and use my addition subtraction properties to bring the like terms together. So I'm subtracting 3x from both sides. 3x minus 3x cancels. So 9 is going to come down. That's going to equal 4x minus 3x is just x, because 4 minus 3 is 1. And then negative 6 just comes down here. Now I'm going to add 6 to both sides because I want to get x by itself. So negative 6 minus 6 cancels out. 9 plus 6 is 15. So now I know what x is, but remember they didn't actually ask me to find x. I needed x because I need to fill in the blanks here. I know f equals 3x plus 9, but if you tried to type that into here, it's not going to let you. Alex wants the actual angle measure. So I needed to know what x was so that I can go back and plug it in. So I know it's 3x plus 9, and here it is, 3 times x plus 9. Well, I know x is 15. I just found that. So 3 times 15, that's 45, plus 9 more, that's 54 degrees. I can do the same thing for G. So here's angle G. Now, we should already hopefully remember that angle F and angle G should be congruent. That means when I worked this problem out, it should be 54. If I get something different, something must have went wrong with my math here, and I need to go back and check, because they should both be the same. Isosceles triangle theorem. Right? So 4 times 15 is 60. 60 minus 6 is 54. So yay! That did in fact work out the way it was supposed to. We have 54 and 54. So now we need to fill in this last angle here, angle H. And we have the triangle angle sum theorem. Remember, the three angles of a triangle have to add up to 180 degrees. If I know what two of the angles are, I can simply add them together. so that I know what I'm using. So 54 and 54 gives me 108. And if I subtract that from 180, I'll know what I'm left over with. What can angle H even be? It can't, remember, they can't go over 180. They have to be 180. They can't be less than, they can't be more. So I have to subtract to figure out what's left over there. So I get 72 degrees. All right, so we have one more problem here. It's our very last proof, and it's about isosceles triangle theorem. So we're actually proving the isosceles triangle theorem, so we're not going to use that as one of our reasons. We're proving it. Okay. So let's go through and mark our diagram here. So if QR is equal to QS, so I'm going to write that in here because it was given to me. And I also have QP bisects RS, so I did that as kind of a dotted line here. So we're going to go given. Now we're going to define segment bisector just like we have in those last few that gave us that same idea. Anytime you're given a word in the given, you need to go back and use that as a definition or use properties with it when we were given parallel. So I know segment bisector means it cuts that segment in half. So QP bisects RS, that means that it's cutting it in half. So I have SP is congruent to RP. And that's because of the definition of segment bisector. So now I need to kind of go through and make my decision. What am I going to do now that I have put my given information in and I've defined segment bisector? What path am I going to take here? So I can either prove all three sides are congruent because I was given two sides. So we can definitely prove something about this third side. Or I would need to prove the included angle here, which is S and R congruent. That's the only other thing I could do with those two sides. There's nothing at all I can prove about S and R. In fact, that's what I want to prove at the bottom. That's where I'm trying to get. So I can't just jump to that yet. There's nothing I can use quite yet. So I'm going to go ahead and use that third side. Since they're both sharing PQ again, it's in between both of them. PQ is equal to PQ. So I'm going to use the reflexive property to show that that third side is congruent to itself. So now we just showed that all three sides of triangle SPQ are congruent to all three sides of triangle RPQ. So we can go ahead and put that down here in our statements. And we know that's true because of side, side, side congruence. All right, now that I've proven the triangle is congruent, I can use that very fun cpctc, corresponding parts of congruent triangles are congruent. So I can even see on my corresponding triangles here down at the bottom, we have R at the beginning and S at the beginning. They're both in the same position. And I can look up here on the diagram, and if it kind of looks like this is a fold line, S and R would kind of fold right on top of each other if we were able to fold those right back over. So angle R is congruent to angle S because they're corresponding parts of congruent triangles. All right, so that was the last slide for this one. I know that was, it's a lot of proofs, and I'll say it again. The more you practice the theorems, definitions, postulates, the more familiar you become with these, the easier it is to see these plans through. You definitely have to be able to plan ahead on a lot of these proofs to be able to know, okay, this is what I'm given, where am I going next? If you don't necessarily know the theorems, postulates, definitions, it's very difficult to plan ahead and actually see that path. So I very heavily suggest that you study the theorem list and make sure that you kind of know or are familiar with them at least so that you have an idea of where you're going. I hope this helped, and I will see everyone after spring break.